So the second derivative test, I first want you to draw these particular cases. So it says here, in addition to testing for concavity, the second derivative can be used to perform simple tests for relative maxes and mins. So I want you to draw a differentiable curve that, remember, that means smooth, with one relative minimum. Oops, that's a highlighter. So I am going to draw with a relative minimum, and it says label this C f of C, like that. And also draw one with a relative, just a single relative maximum. To make it simple here, it has to be smooth because it says it's differentiable, right? At the relative minimum, what do you know about the value of the second derivative, and how do you know this? So look at the whole drawing, right? If I drew this and it can only have one relative minimum, I can see at this point here, and it has to be differentiable, that if it's smooth like that, it's going to have to be concave up. Concave up, which means f double prime of C has to be greater than 0. And in this particular case, if I was to draw something that's differentiable, that means smooth, and only has one relative maximum, the only way that that can happen is if the function is concave down. And it's curved. Obviously, if we did linear, it's not going to be helpful here, right? So here, we are going to, and it has to have a relative, so it definitely has to be concave down. So here, concave down. So that means the second derivative at C would then have to be less than 0. Well, that's basically what the second derivatives test tells us. It says, let f be a function such that f prime of x is equal to 0, and the second derivative of f of x exists on that open interval. That means if f double prime of C is greater than 0, you have a relative minimum. So it tells us that there's a relative minimum if that happens. And if it's less than 0, so that means it's concave down, it must have been a relative maximum. If the second derivative is 0, then the test fails. That is, we have to check it in some other way. All right, so the proof for this is, we're going to start with if f prime of C is equal to 0, and f double prime of C is also equal to 0, then there exists an open interval I containing C such that f prime of C, f prime of x minus f prime of C over x minus C is equal to f prime of x over x minus C, because f prime of C was equal to 0. So you can substitute that 0 in here. So that's a 0 there, right? And this here. For all values here. So I think I wrote that wrong. Hang on. I think this was supposed to be like this, is greater than, like that, right? Because that's here, this is then the average rate of change. If it's concave, in this case, the second derivative is greater than 0, that means it's concave up, right? So that means that the average rate of change, if it's concave up, is then always going to be greater than the second derivative, just as a side note here, as far as I can remember. And then if x is less than C, then x minus C is less than 0, and f prime of x is less than 0. That means then if x is greater than C, then x minus C is greater than 0, and f prime of x has to be greater than 0 for that to be the case. So if f prime is changed from negative to positive, so f prime changed from negative to positive at x is equal to C. That's the only thing, right? So if I'm picking values to the left of C, so I'm substituting in values for x to the left of C here, then x minus C, that denominator is less than 0. So then the first derivative is less than 0. That means the function is decreasing, right? F is decreasing. And if x is greater than C, then the denominator down here ends up being greater than 0. And f prime of x has to then be greater than 0 for this to be true, that this remains 0. So that means then that f prime of x changed from negative to positive at x is equal to c. And because the function is differentiable everywhere, that means that must have been a relative minimum there. So by the first derivative test, f of c must have been a relative minimum. And then similarly, you can prove the relative maximum by the same thing. But the only thing that changes here, the proof for that, is that now it's going to be f prime of c is equal to 0 and f double prime of 0 is less than 0. F at c, sorry, double prime of c is less than 0. So then you can always try that. And then you just look at what happens right before you get to c. If I substitute in x values right before c and x values right after c. And what it forces then the first derivative to be, because then it tells you then hopefully that the function increased and then decreased. So that would give me a relative maximum. All right. So the best way to do this is just to try some problems, right? So if I wanted to find the relative extremas using the second derivatives test, I would take the first derivative and find the critical values, because essentially I'm taking, if you look at it, it says wherever f prime is equal to 0, I'm going to test those in the second derivative. So we take, this is how this functions, take critical numbers of f of x, where f prime of c is equal to 0, and test in second derivative. That's essentially all we're doing. So my first job is to find the critical numbers. So first derivative, take that first derivative and set it equal to 0. So those are the critical numbers. So I do a little bit of factoring as well. So my critical numbers are x is equal to 0, negative 1, and 1. I take those values and then try to substitute them into the second derivative. That's really what the second derivative test tells me to do. So I'm going to have to find the second derivative. And then take those, here's my second derivative, just using the power rule again, right? So for first derivative, we used the power rule, did a bit of factoring to make it easier to find the critical numbers. But now I just have to substitute those critical numbers into the second derivative. So we're testing the critical numbers. So look, I am testing negative 1, 0, and 1 in the second derivative. And what I'm looking for is not necessarily the value, I'm looking for the sign. So the first one, I see that I'm getting a positive. If I get a positive second derivative at a critical number, I know that the function was concave up there. So it was concave up, and we had that point down here at the bottom. So that point down there, that's going to be a minimum. So I know that this right here at x is equal to negative 1 must have been a minimum. That's the only way that this could happen like that. At f double prime of 0, we ended up getting a 0. So this one is a little bit more shaky. What do we do, right? I have to test that. And f double prime of 1 is negative, so that means it's concave down. So that point must have been up there at the tippy top. It must have been a maximum. So we end up with a relative minimum. Where it's equal to 0, it can't be determined. I have to do it in a different way. And a relative maximum. So let's look at what we can say, though. We only need to check where it can't be determined. So if I already have the first derivative, I'm going to check surrounding just the 0. I don't need to check what's happening over here. I don't need to check because I already know that right here at x is equal to negative 1, it's a relative minimum. And at x is equal to positive 1, it's a relative maximum. So really all I need to concentrate on and test is surrounding the 0. And I can see that, and I'm testing in here, the first derivative, test first derivative. But I'm only doing that if I need to. So in this case, I just need to test around that. And it's neither a max or a min at x is equal to 0. So then if I'm looking for the extremas, all I need to worry about then is at -1 and at 1 then. So then to find the actual extrema, I have to find the order pair. So I substitute in -1 and 1 to the original function. So I know that f of x has a relative minimum at the point -1, -4, since f prime, so my reasoning changes, right? I state that the first derivative is equal to 0 there, and the second derivative is greater than 0. That is the second derivatives test. That I'm using the second derivatives test to reason it out. And f prime of x is a relative maximum at the point 1, 4, since f prime of x is equal to 0, and f prime of x was less than 0 at 1. So it changes the reasoning. It's a little less writing than if we use the first derivative test where we have to have the 3 reasons there. So now I want you to pause the video and try part B, and I'm going to reveal the answer all worked out for you in a second. So pause and try B. So first derivative, set the first derivative equal to 0, test those values in the second derivative. In this case, you didn't end up with a point that was like not determined, so then we already know. All we have to do, we have a relative max and a min, which happens. And I worded it slightly different. In the first, in part A, I wrote it as an order pair. It's just kind of stylistic thing, as an order pair, whereas here I wrote it as a sentence. The maximum value of 33 happens at x is equal to 2. You could also have written it as an order pair. It's just a stylistic thing.